Good morning, ladies and gentlemen. My name is Siregar from Atmajaya Catholic University. Today, we want to present our paper with the title A New Method for Reducing the Cogging torque in a Permanent Magnet Machine of Integral Short Number for the Renewable Energy Plant Application. The paper outline is Introduction and Purpose, Permanent Structure, Research Method, Cogging torque calculation, Performance simulation using finite element method, and discussion and conclusion. Recently, the permanent magnet machine have used widely in many applications. Why? Because there's the advantage. The advantage is high efficiency, compact, easy maintenance, good reliability, and excellent efficiency. Based on the purpose, we develop and propose a new method of cogging torque reduction by employing the two steps of slotting in magnet each. One, with the target that the design and the result must be used for the geothermal application as a high-speed permanent magnet machine. This is the permanent magnet machine structure for the original structure or for our proposed. Figure 2 is our proposed. Our proposed, as we said, by using employing the slotting method. On this paper is by using the two-step slotting in the magnet edge of the permanent magnet machine. We use this machine with the characteristic with the number of 48 slot and 6 port. We select the slot opening width of 2 mm and the distance between the whole magnet rotor surface and the stator core is 2.28 mm. As I said, that we use the simulation by using response surface method and finite element method. On this paper, we use the parameter for that machine as we test for initial structure, for one-step slotting and for two-step slotting. Of course, the focus is for two-step slotting. The name of parameter we can show here: stator diameter. The second is air gap length. The next is rotor teeth angle, slot opening. As we say, we use 2 mm, sub diameter, magnet length, magnet height, and air gap cross section. This is the formulation for the cogging torque reduction. Equation 1 is the TC is the cogging torque itself. Flux G is a air gap, magnetic flux in the air gap. Rg is a air gap reluctance. Theta is the rotor position. So based on the situation, we can find the cogging torque itself. And flux density also we can find the air gap reluctance. So here we see in the equation 2. By using equation 3, this is of course by using the Fourier series, we can find also the cogging torque, where the M is the least common multiple of the number of stator slot and the number of the pole. So K is as an integer, and Tm is the Fourier coefficient. Also, by using, we know what is the material of the magnet itself, so we can find, after we know the magnet cogging coefficient, so we can find also the cogging torque by equation 4. Here also in the equation 5 we can see that air gap reluctance we can find by using the equation 5, where is then the magnetic itself also we can calculate by using equation 6, where here is BR is a magnetic remanence, LM is a magnetic length, RR is the rotor radius, and LG is air gap length. So by combination equation from 4, 5 and 6, we can find the Cogging torque calculation by equation 7. This is the simulation result of our method. So you can see here the flow of the flux magnetic from rotor to stator. So here we see that how the fate of the flux from rotor to stator in the original structure, and also in one-step slotting and in two-step slotting. This is the comparison of normal flux distribution in our result. So the left one is the initial one, and the second is the proposed one. We can see here that in the proposed one there's no distortion. Then also in the comparison of tangential flux density, we can see also that in the initial one the curve is in the both. You can compare that in the proposed one is a little bit not distortion. This is the comparison and normal magnetic distribution for three model is original, one-step slotting, and then two-step slotting. Here we see that the value of magnetic B, we can see in the original structure is 1.48. The second one is a one-step is a 1.209, and then in the two-step slotting 1.20968. So this is the data, the output that to show that in the two-step slotting we can see that the magnetic B will be smaller. This is the comparison of Cogging torque between the initial structure and one-step slotting and two-step slotting. We can see in this curve that the blue one is the initial structure, the black one is one-step slotting, the red one is the two-step slotting. This curve we calculate or we investigate within 180 mechanical degree, but in this paper we show in the curve only 60 degree of mechanical degree. Yeah? We can also see from this curve the maximum for the initial structure is around 0.5 or close to 0.6. In the one-step slotting is the maximum CT is around 0.06, and in the two-step slotting the maximum of CT is 0.002. So we can see from this result that Cogging torque reduction we can find around 98.8%. So this is a good result. So based on this result, we find that based on the discussion that the proposed method will reduce the cross-section area of the magnet without changing the rotor diameter. Also, this proposed can be inferred to modify and reduce the magnetic flux strength without any change in the magnetic material of the insert permanent magnetic machine. Also, this method will decrease the reluctance of the air gap as an important parameter that influences the Cogging torque in PMM. The magnetic flux density of the proposed machine in the stator and rotor also decrease when compared with the non-slotting design in the magnet edge. So we can conclude the smaller cross-section area of magnet pole result in the decrement of cogging torque and air gap normality in the permanent machine. Additional slotting in the magnet edge reduces the magnet pole cross-section and the cogging torque. The novelty of the proposed two-step slotting achieves to adjust the magnet pole arch and distance without changing the rotor diameter and stator. The air gap between stator and rotor core can be increased to reduce the air gap reluctance in the machine. And the flux circulation in the surface of rotor teeth will reduce the cogging torque in the air gap effectively. So finally, we can say that by employing the numerical computation based on the finite element method, it has been found that the cogging torque reduction of the proposed is 98.8%. So with this condition, it might be used for the reference for the design and construction of the permanent machine for the renewable energy plant as for the geothermal plant application. Thank you for your attention.